All right, BC Calculus, this is your series review for your test. Remember, there's only certain things they're going to be asking this year. So there's four types of series that you need to know for the test: geometric, P-series, alternating series, and harmonic series. Now, some of these overlap. So for instance, an alternating series can be harmonic. You could have an alternating geometric series, an alternating P-series as well. The harmonic series is a P series where this P is 1, because if P is 1, 1 over n to the first power is just 1 over n, which is the harmonic series. Remember, the harmonic series always diverges unless it's alternating, and then the alternating harmonic series converges. So there are some overlaps between these four things. So remember, a geometric series has a common ratio. So you're looking for some r raised to a power n. It could be n plus 1. This could be written as a fraction as well. But the geometric series converges when that ratio, the absolute value of that ratio, is less than 1. And it diverges when the absolute value of that ratio is greater than or equal to 1. When the geometric series does converge, you can also find the sum of that, which is a1 over 1 minus r. Remember that you can only use this formula here to find the sum if your ratio is less than 1. If it's bigger than 1, you'll get a number here, but it'll be wrong because you're not allowed to use this sum formula for convergence. Okay? So a geometric series, if you write out the first three terms, you should see that you're multiplying by the same thing to get to the next term. So for instance, 1, 2, 4, 8, 16, etc. That's a geometric series with a ratio of 2, which is greater than 1, so that series would diverge. But that's how you recognize a geometric series. Okay? P series is 1 over n to the p. This is the one that converges when p is greater than 1, but diverges when p is less than or equal to 1. Remember, for the alternating series, look for negative 1 to the n, or negative 1 to the n plus 1, or negative 1 to the n minus 1. Or a tricky way of writing an alternating series is cosine pi n, because if you plug in, say, n is 0, cosine of 0 is 1. When you plug in n is 1, you get pi, and the cosine of pi is negative 1, so it'll go 1, negative 1, 1, negative 1, just like this series does up here. So this is kind of a sneaky way of throwing in an alternating series. Okay? And remember, an alternating series will converge only when these two things are true. So the terms have to get smaller in absolute value, and the limit as n goes to infinity of that series has to equal 0. And if those two things are not true, then you know the alternating series will diverge. Okay. And then harmonic series we kind of already talked about. So remember the tests, you may have to do the ratio test. You can set this up on any type of series if they ask you to do that, and this will converge when the limit as n goes to infinity. You take the original series and replace n with n plus 1, and then you divide by the original series, and the absolute value of that is less than 1. Okay? And remember, if this is a fraction, rather than divide by the original series, just multiply by the reciprocal or the original series flipped over when you do this, and then group and simplify those as well. Okay. And then the other thing they may ask, or they probably definitely will ask you this year, is how to construct a Taylor polynomial. So this is the Taylor or Maclaurin series polynomial construction. Remember, the only difference is whether it's centered at 0 or not centered at 0. So this is the general one for any a where a is the center. So it's the original function value at that point, and then it's the first derivative, the x term to the first power divided by 1 factorial, and then the second derivative, the x term squared over 2 factorial, the third derivative, x to the third over 3 factorial, etc., etc., etc. And this is the general term where n could be any number as well, at all. Okay. So remember, if it's centered at 2, then instead of being x, this will all be x minus 2 squared, x minus 2 to the third, etc. And if it's centered at 0, you don't write x minus 0, that's just x. Okay. All right, that's the cheat sheet that I want you to have printed out. And then I would probably print these problems too as examples, because they're good examples here. Okay. So first of all, I should probably mention that I stole this from the people that are doing the AP review sessions online. So thank you, Brian Passwater, for these problems. This is the same thing that he's posted on the AP review site that I haven't been having you guys do because I've just been selecting problems out of there that I think are good problems that'll show up. Some of his stuff is pretty tough on here as well, which you'll see on some of these, okay? All right, so they're given two series. So the first thing you should do when you're given a series is, well, what kind of series is this? Hope you recognize right away. And I want you to pause the video as we go through this video to kind of together and see if you can work this out. So, or I'll just pause and tell you I'm going to pause here. Okay, so what kind of series is A and what kind of series is B? Okay, well, A, you should hopefully recognize this -1 to the n is the alternating term, so this is an alternating series. It's also a p series because you have n raised to a power in the denominator. So remember, some of these will overlap. So this is an alternating p series. Probably going to focus just on the fact that this is alternating, though, and maybe look at the p series as well. This one is not alternating, so this would just be a p series. Okay. All right, so A is probably the easiest thing they can ask because they're telling you exactly what to plug in for P. So P is 2.5. So that means AN, this series AN is equal to -1 to the n over, if I plug in 2.5 and I minus 2, I get 0.5. And hopefully you recognize that the power of 0.5 is the square root of n. So that really is this when P is 2.5, okay? And then this one, when I plug in for Bn, this will be -2, is always there on top. And then 6 minus 2.5 is 3.5. So we'll go ahead and call that. Okay. Now the fact that there's a -2 up here really doesn't matter. We're really just focusing on the fact that this is 1 over n to the 3.5. Okay. So we're showing that both of these converge. So this is an alternating series. I'm going to use the alternating series test on this one. So for short, it's AST, or alternating series test. Remember, you need to show that two things are true. One is that the terms decrease in absolute value. So for instance, if you plugged in 1, you get 1 over square root of 1, which is 1. So 1 over 1 gives you 1. Actually, it'd be -1. We're going to ignore the alternating one. If I plug in 2, this would be 1 over the square root of 2, then 1 over square root of 3, 1 over square root of 4. So the terms are getting smaller in absolute value. And if I do the limit as n goes to infinity on this, so the denominator is going up faster than the numerator because the numerator is just alternating back and forth. It's not going up or down at all. This denominator is going up faster, and when the denominator goes up faster, it goes to 0. So you just need to say or type out, or for the calculus test, I want you to write this out. The limit as n goes to infinity goes to 0, and terms decrease in absolute value. So therefore, it converges by the alternating series test. Okay. For this one, this is a p series where p is greater than 1 because 3.5 is obviously greater than 1. If you go back to the cheat sheet that you had at the beginning, remember p series converges when p is greater than 1. So all you would have to say is converges by p series test. And then if you wanted to put in there where p is greater than 1. Okay. So again, that's kind of a simple one. That's as simple as they get. The biggest thing is recognizing, hey, this is an alternating series. This is a p series. Use those two tests to determine whether they converge or diverge. In this case, you're just showing that they both converge. Okay. All right, for the next one, we're going to find all the integer values of p. So rather than be given a p like we were up here, we are going to find the value of p that'll make both of these things converge. Okay. So for AN, which is the alternating series, we know that this will only converge when the terms decrease in absolute value. Okay. If the terms are increasing in absolute value, then it will no longer converge by the alternating series test. So for that one, we need that exponent here, which in this case is p minus 2, to be greater than 0. Okay. Which, if you add 2 to each side and solve for p, you get p is greater than 2. Okay. So now, if I check that, if p is equal to 2, 2 minus 2 is 0, and anything to the 0 power is 1. Well, that would just give you 1 for forever, which means the terms aren't going to 0, and they're not decreasing in absolute value because they would just alternate back and forth between -1 over 1 and then +1 over 1, etc. So p has to be greater than 2. Okay. Now, if you looked at a negative number, so let's just look at -1 for p. -1 minus 2 is -3. N to the -3 would mean it's no longer a p series because that negative exponent would flip this n up here and make it n to the third power up here, which again is no longer a p series. And for alternating series, the terms would not decrease in absolute value because now that the n terms in the numerator, it's just going to continue to grow and grow and grow. So for that one, p has to be greater than 2. So that one's a little bit tricky. You may need a second to wrap your head around that one. For this one, we're just going to, again, look at the p series. So 6 minus p has to be, in order to converge, it has to be greater than 1. And then if I solve this by subtracting 6 and subtracting 6, I get negative p is greater than 1 minus 6 is -5. And then get rid of this negative divided by a negative. Remember, when it's an inequality, you got to flip the inequality around, and p has to be less than 5. Okay. So we're looking for the integer values that are bigger than 2 but less than 5, which would be 3 and 4. So for this one, p equals 3 or 4. Okay. And this is kind of your justification here that we did, or that I showed you there. All right, for this next one, again, they told you the p-value, so we're letting p equal 4. So for the first one, we have an equals -1 to the n. And when I plug in 4, I get n squared here because it's 4 minus 2 gives you 2. For bn, I have that -2 on top. And then when I plug in p is 4, 6 minus 4 gives you 2, so that'll be that one. Okay. All right, so I let p equal 4. Then f of x will be a function with derivatives of all orders at x is 2. So that means that's my center at x is 2. The f of 2 is equal to -3. And this is a generic function for the derivative. So f to the n, that'll be the first derivative when n is 1, the second derivative when n is 2, the third derivative when n is 3, etc., etc., is equal to n factorial times an for n greater than or equal to 1. Find the, remember this notation means the third degree Taylor polynomial. So p sub 3x means the third degree, which means I'm going up to the x to the third term. And I'm centered at x is 2, like I said up here. Okay. So this is just about finding the derivatives and writing it out. So for the third degree Taylor polynomial, I need the third derivative. So the first derivative was when n is 1. So I plug in n is 1 here. So the first derivative at 2 is equal to 1 factorial, and then a to the first. Well, 1 factorial is 1 times a to the first is just a to the first. And when I plug in, n is 1 to a to the or a to the 1 here. -1 to the first is -1. N squared is 1, and -1 over 1 gives you -1. So that's your first derivative. Second derivative at 2. Now I'm plugging in 2 over here. Well, 2 factorial is 2. And a sub 2 would be this one. -1 to the second power is +1. And 2 squared is 4. So that'll be 1/4 times 2 factorial, which is 2. And 2 times a fourth is 1, or 2 over 4, which is 1 over 2. And then the third derivative at 2, plugging in 3. 3 factorial is 6. And -1 to the third is -1 over 3 squared is 9. So if I do that little math up here, I got 6 times -1 over 9. And 6 over 9 reduces to 2/3. So that'll be -2/3. Okay. Once you have the derivatives, you should be able to write your Taylor polynomial. So remember the Taylor polynomial, and this is on that cheat sheet at the bottom, is the function value, which is -3, and then plus, but it's minus or negative, so it'll be minus the first derivative, which is 1, and then x minus 2, since they're centered at 2 to the first, over 1 factorial. You don't have to write the 1 factorial, which is 1. You don't have to write this one out here. You don't have to write this one as an exponent, but if you want to, that's totally okay. And then plus the second derivative, which is 1/2 x minus 2 to the second divided by 2 factorial, and just leave it like that. And then plus, but again, it's negative 2/3 x minus 2 to the third over 3 factorial. Unless there's some reason, just leave it like that, and that's your answer. All right, for part D, using the third degree Taylor polynomial that I just found in part C, find the first derivative of that. So let's go ahead and do that, and that should be the easy part, or pretty easy part. Okay, so the derivative of -3 is 0. Doing this will be -1. This is power rule with chain rule, but the derivative of the inside is just going to be 1. So the 1 would come out front. Subtract 1, you get 0, and anything to the 0 power is 1. So the derivative of this is just -1. Okay. All right, plus, let's just go ahead and keep the 1/2 there. You put the 2 out front. X minus 2 stays the same to the first power. Times the derivative of the inside, but again, that's just 1, and then the 2 factorial will stay there as well. Okay. And then minus 2/3 times, put times there too. This time you're putting the 3 out front. X minus 2 to the second times the derivative of the inside, which again is just 1 over 3 factorial, would just stay there. All right, and that is your derivative of this. Okay. And again, you could simplify this, but if you don't need to, if there's not a good reason to, then don't worry about it. All right, now when x is 3, the series given by this, sum from 1 to infinity of Cn, is a p-series whose first 3 terms correspond to the first 3 terms of p, the derivative of p3x. Determine whether Cn converges or diverges when x is equal to 3. So all I have to do is plug in x is 3. Here I'm going to have to do a little bit of math and see what I get. So p prime sub 3 at 3 is equal to this series, which they're calling Cn. So the first term will be -1. When I plug in 3 here, 3 minus 2 is 1. 1 to the first power is 1. This 2 will cancel this 2 out. So I am left with 1 over 2 factorial, which is plus 1 over 2. For this one, when I plug in 3, 3 minus 2 is 1. 1 squared is 1, so this just kind of goes away. These 3's will cancel. 3 factorial is 6, and 2 over 6 reduces to 1/3, so this is -1/3. So hopefully you can notice now this is an alternating series. Now they kind of threw you off that this is a p-series as well. Well, it is, because this is actually the alternating harmonic series, because if I kept going, so plus, the next one would be positive 1/4, and then minus 1/5, plus dot 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 plus, and this is just alternating, so there's -1 to the n over n, because n goes 1, 2, 3, 4, 5, etc. So you could just say that this converges by alternating harmonic series. And if you say that, you don't have to say the two things for alternating series. If you just said converges by alternating series test, you would have to say the two things, which is the limit as n goes to infinity, goes to 0, because the denominator is going up faster than the numerator, and the terms are getting smaller in absolute value because 1 is, or a half is smaller than 1, a third is smaller than a half, a 1/4 is smaller than 1/3, so the terms are getting smaller in absolute value. Okay. All right, so very typical problem. This is probably the difficulty level that I would expect to see on the test, is this problem. So this is actually a really good problem. All right. Scroll down to the second one. This one I just have a series AN, where AN is given by 5 x plus 3 to the n power over -6 to the n. So again, just looking at this series, well, it's not harmonic. It's not a p-series because you have an n term here on top, and remember P series is n to a power, and here the n is the power, so this is not a P series. Depending on if I plugged in something for x, this could be a geometric series, and this is potentially an alternating series because of this negative 6 to the n power. It doesn't really matter if it's at negative 1 to the n. It's in the denominator, which is a little bit different, but so right now this is just kind of what we call a general series. So depending on what we do with the value we plug in for x, that might change what type of series it is. But for right now, just look at this and go, okay, this is just kind of a general series, and we'll see where it leads us. Okay. All right, so first one, determine whether the series converges or diverges when x is 1. So again, we're actually plugging in 1 here now. So when I do that, I get 5, and then this will be 1 plus 3 is 4 to the n power over negative 6 to the n power. Okay. Now you could actually group this together as, we can just pull the 5 out front, and you can group this as 4 over negative 6, which is negative 2 over 3 if you wanted to do that, raised to the n power. Because I can group those two things together with just one n power as a fraction like that. And that's actually helpful to do because now hopefully you can see what kind of series that is, and it looks like it's a geometric series because this is your ratio raised to a power. So this is r raised to a power. So for this one, your r, or your absolute value of r, is less than 1 because 2/3 is less than 1. So this will be a converges by geometric series. Where r, absolute value of r, is less than 1. All right, this next one, now this series is equal to L. Usually they use L as some limit. So this is actually another way of saying this is converging to L. Okay? And L is 15. So the only one that actually converges to a given value is the one that we can find the sum of, because that sum is going to be, in this case, 15. So the only one that converges to a sum is the geometric series. So remember, the sum for a geometric series, the formula that's on your cheat sheet, is A1 over 1 minus R. And A1 is the first term. And for the first term, you need to look at what we're plugging in here, which is 0. So if I plug in n is 0, anything to the 0 power is 1, times 5 will be 5. Again, anything to the 0 power here is 1, so 5 over 1 gives you 5. So I know A1 is equal to 5. And then it's over 1 minus the ratio. And the ratio is just this term here, which is x plus 3 to the n power over negative 6 to the n power. That's your ratio. And when we fixed x, it was the 2/3, but here we're actually solving for x here. So the ratio is x plus 3 over negative 6. And that has to equal 15. So the fun part is trying to solve this because it involves some tricky algebra here. So this is probably a little bit more tricky than you'll see on the AP exam. They probably wouldn't give you a fraction here, but so what you have here is a fraction. So to add fractions or subtract fractions, you need a common denominator. So your common denominator is going to be, let's go ahead and make it, well, negative will end up becoming positive. So let's go ahead and make it 6. So we have 5 that stays the same. We'll change 1 to 6 over 6. And then plus, this will be x plus 3 over 6, because again, negative will give you plus there. So now I can add those together. So 6 plus x plus 6 will be x plus 9 when I combine like terms of 3 and 6 over 6. And then rather than divide by a fraction, I'm going to take that and multiply by the reciprocal. So that's the same as 5 times 6 over x plus 9. 5 times 6 is obviously 30, so I get 30 over x plus 9. sorry, x plus 9, and again that equals 15. X plus 9, there we go. And now we're solving this. So if I switch these, I get 30 over 15, which is 2, is equal to x plus 9. Subtract 9, you get x is equal to negative 7. So this is the value of x that I would plug in so that my limit or my sum actually goes to 15. All right, so remember the geometric series is the only one where this sum can actually equal a number. So, and this is the formula. All right, so let dn be equal to an over n plus 1, find the interval of convergence. So when they ask you to find the interval of convergence, they're talking about the ratio test here. Okay. All right, so we always start off the ratio test with the limit as n goes to infinity. Again, this is on your cheat sheet. This one will be a fraction, so it'll be the absolute value of, I'm going to be replacing n with n plus 1. And I need to piece this an together, which is this thing up here, with the dn part, which is n plus 1, or over n plus 1. So the 5, x plus 3 stays the same. Remember, replacing n with n plus 1, so this exponent that was n up here becomes n plus 1. Over this n on the bottom also becomes n plus 1, so it's negative 6 to the n plus 1. And then this one that's n plus 1, well, if I replace n with n plus 1 and then I plus 1, I get n plus 2. So that's replacing n with n plus 1, since this one's a fraction times the original one flipped over, which will be negative 6 to the n, and then 5, x plus 3 to the n, and then this n plus 1 will also get flipped over and go to the top like that. And the absolute value of that converges when this is less than 1. All right, now we're going to group these by like terms. So remember, put the n terms out front. So my n terms are that just involve n are n plus 1 and n plus 2. So I'm going to do the limit as n goes to infinity of n plus 1, n plus 2. For the 5s, those will cancel out, so that'll go away. Here I have x plus 3 to the n plus 1 over x plus 3 to the n. So this plus 1 means I have one more x plus 3 on the top. And remember, you only need to put the absolute value around the x term. So, and that'll be on the top. You have negative 6 to the n over negative 6 to the n plus 1. So you have one more negative 6 on the bottom than you do on the top. So that'll give you negative 6 on the bottom, and that converges, or you'll find the interval of convergence when that's less than 1. Okay. Now I do the limit as n goes to infinity. As n goes to infinity, if on this fraction, the top and the bottom are going up at the same rate, so you ignore the plus 1 and plus 2, and n over n just gives you 1. So all of this just becomes 1, which means this is just absolute value of x plus 3 over negative 6 is less than 1. And now you're going to be solving for x. So you'd multiply by negative 6 to get rid of the negative 6 and get rid of the fraction. So absolute value of x plus 3 is less than, multiply by negative 6, you get negative 6. And then remember, with absolute values, you have two different equations. You have x plus 3 is less than negative 6, and then you have x plus 3 is greater than positive 6. And then you solve this, so you subtract 3, you get x is less than negative 9. Subtract 3, you get x is greater than 3. And I just forgot, the absolute value goes around this whole thing. So this isn't negative 6, it's positive 6. So scratch that out. Positive 6, flip it over, makes it negative 6 here. So subtract 3, you get x is less than 3. Subtract 3, you get x is greater than negative 9. I knew I was going wrong here because less than negative 9 and greater than 3 would not come together, because if you did a number line, negative 9, less than negative 9 would be that way, positive 3 would be that way. The interval of convergence will never do this, so they always have to come together. All right, so now greater than -9 would be this way, less than 3 would be this way, so they are coming together in between -9 and 3. So your interval of convergence is -9 is less than x is less than 3. Okay. So let's do a couple other things. I don't think they're going to have you check the endpoints, but let's go ahead and do that anyway. So if I plugged in 3 here to the original one, I would get 3 plus 3 is 6. 6 to the n over -6 to the n. That actually becomes an alternating series. So the terms will actually decrease in absolute value because of this n plus 1 here on the bottom. This n on the bottom is going to make a decrease in absolute value, and the bottom is going up faster, so it'll go to 0. So it does include 3. Okay. If I plugged in -9, -9 plus 3 is -6 to the n over -6 to the n. Well, guess what? That's just 1. So in that case, the terms are not going to decrease in absolute value. So that does not include -9. Okay. And again, they said they're not going to ask about that on the test, so you probably should not have to worry about that. But if it does happen to say that, and I missed something on what they said, then go ahead and do that. Okay, so now I'd like to know the center of that. So between -9 and +3, there's a distance of 12. So the center would be half of that, which would be 6 each way. So if I go -6 plus, or sorry, -9 plus 6, that would take me to -3. And then 3 minus 6 takes me to -3. So my center is -3. Well, guess what? From up here, I should have known that because x plus 3 is centered at -3, right? And that means the radius of convergence, or ROC, is equal to 6 because I went 6 each way from the center. So those are a couple other things that they could potentially ask you about on the test. All right, for part D, let f of x be the function that's twice differentiable. That just means I can take the derivative twice. If the first 3 terms of the series Dn are the second degree Taylor polynomial for f of x centered at x is -3, find f double prime at -3. So what I need to do is construct my Taylor polynomial. So, and I'm doing this by the summation this time. So the sum of dn is equal to, well, when I plug in 0, I get 5x plus 3 to the 0 power over -6 to the 0 power. And then remember, we have that n plus 1 on this d from part C, which gives you that. And then I plug in 1 for n. And that's the second term. And then the third term would be, the third term is plugging in 2 since I started at 0. So it'd be 5x plus 3 to the second power, -6 to the second power, and then 2 plus 1. Okay. Those are the first 3 terms. Now remember, the first 3 terms is different than the third degree Taylor polynomial. If this was a third degree Taylor polynomial, I'd have to go to the x to the third term. That's why this is the second degree Taylor polynomial, but it's the first 3 terms of that because I'm starting here at n is equal to 0. Okay. All right, so what I need to know is to find the second derivative at -3. The second derivative is always what's in front of here divided by 3 factorial, because that's how I construct it. It would be the second derivative, the x term squared over 2 factorial. So I know the second derivative divided by 2 factorial is going to equal what I have right here. Okay, so what I have right there is I have the 5 on top. I don't need to worry about this term because the construction is just going to involve all of that. Okay, so the 5 will be there. -6 squared is 36, and 2 plus 1 is 3, and 36 times 3 is 108. I remember if you have a calculator at home, just in case you need to do that math, have a calculator handy or pull it up on your device and plug that in if you can't do that in your head. Okay. So now to solve for the second derivative, I would multiply each side by 2 factorial. That'll get rid of that. And 2 factorial is just 2. So that's just equal to 10 over 108. That's what the second derivative is equal to. This reduces, but again, you don't need to reduce it, so I would just leave it your answer like that. Okay. All right. Next, we're going to do some graph or table problems and then graph problems as well. So you can do series with tables and graphs, and these are good examples of that. And that's a very potential that you'll see that kind of problem this year with tables and graphs, because that's not something that somebody could just randomly look up on the internet. So here's obviously our table problem. We have a table of x values at x is 1 and 4, and we have the function value, the first derivative, the second derivative, and the third derivative at both x is 1 and x is 4. Okay. Functions f and g are differentiable for all orders at all x values. Selected values of f and several of its derivatives are given in the table above, and now g is this equation here. So we have a table of f values and an equation of g here, which is related to the f because it's the integral of f here as well. All right, so find P3x, the third degree Taylor polynomial for f centered at x is 1. Well, this one is what I consider an easy one. So the third derivative, the third degree Taylor polynomial at x is 1 is going to be these values right here. And this is f, and this is a table of f. So I just need the function value at 1, which is -2. And then plus the first derivative, which is 0. And then x minus, centered at 1 would be x minus 1 to the first over 1 factorial. Okay. Now, obviously, I didn't need to write that, but just to keep going, I think it's actually easier to write that term. And then it's the second derivative, which from the table is 3, x minus 1 squared over 2 factorial. And then the third derivative, 4, x minus 1 to the third over 3 factorial. And you can leave your answer like that. Okay. And again, I would leave my answer like that. Even though 0 times anything is 0 and this whole term goes away, I would go ahead and write this, because remember, it's function value 1, 1, 1, second derivative 2, 2, 3, 3, 3, 4, 4, 4, etc. And it just follows that pattern. Okay. All right, so for part B, I'm doing the third degree Taylor polynomial for g now. Well, this one's a little bit harder because I'm not given the first derivative, second derivative, the third derivative that I need to construct the Taylor polynomial like I had up here in this table for f. They switched to t, but they could have said p as well. They just switched variables because we did use p up here, so to make it different, they used t down here. Okay. So now I need the function value at 1, so g at 1. So here I have to work for it. It's not hard, it's just not as easy here because they gave me everything, and here I got to do a little bit of work for it. So when I plug in 1 here, I get 3. When I plug in 1 here for this x, because this is 4x, just in case you can't see it, I get 4. And the integral from 4 to 4 is 0, so 3 plus 0 just gives you 3. And then the first derivative at 1, well, the first derivative of this is going to be 3 plus the derivative of this. So this is fundamental theorem of calculus. The derivative of the integral is just this function f. When I replace the dummy variable t with 4x in this case, remember chain rule applies, so I got to times that by 4. So that's the first derivative. When I plug in 1, I get 4 times 1 is 4. F at 4, oh, well, I got to get that from the table, is -9/4 times 4. I'll cancel that 4 on the bottom, which gives me -9, and 3 plus -9 gives you -6. Okay. So I got to do a little bit of work. And that was g prime. Okay. Now g double prime, well, the derivative of 3 is 0, so luckily that goes away. For the derivative of this is going to be chain rule, so the 4 will stay there. The derivative of f of 4x is f prime 4x times the derivative of the inside is 4 for the chain rule, which is going to give me 16 f prime 4x. And now again, I'm plugging in x is 1 because that's what it says to do here. So this is 4, and f prime at 4, well, that's why I have this, is 3 halves, and 16 times 3 halves is going to give me 16 over 2 is 8, times 3 gives you 24. So the second derivative at 1 is equal to 24. And now I need the third derivative. But you can see why they would ask this type of problem, because they're testing, do I know how to use a table? Do I know the fundamental theorem of calculus? Do I know how to take the derivative of this and get values out of the table? So they're testing a lot of things when they ask this thing in part B. Okay. So the derivative of this, again, is going to be the 16 will stay there. If I do the chain rule, that'll be times 4, which will give me 64. F double prime 4x. I did that kind of quick, but hopefully you can do that. And then f, plug in 1, you get 4. So f double prime at 1, I'm sorry, f double prime at 4 is equal to negative 9/4. So this will be 64 times negative 9/4, which is why you want to have a calculator handy. So 16 over 4 is, or 64 over 4 is 16, and 16 times 9 is 144, and it'll be negative, so g triple prime at 1 is equal to negative 144. All right, now I'm ready to construct my Taylor polynomial. So it's the function value, which in this case is 3, plus, but it's negative, so it'll be minus. The first derivative, 6, x minus 1, since I'm centered at 1 to the first, over 1 factorial, which you don't have to write, but I do, plus the second derivative, which is 24, x minus 2 to the second power over 2 factorial, plus, but it's negative, so minus 144, x minus, sorry, I don't know why I wrote a 2 there, 1 to the third power over 3 factorial. And again, unless there's a good reason to simplify that, just leave your answer looking like that. All right, for part C, let the summation of AN be a geometric series whose first 4 terms are the 4 terms found in part B here. So I got my first 4 terms here. Find the sum of AN where x is equal to 5/4 or show that the series diverges. So I know it's a geometric series, so I need to find out what that ratio is. So like I just said, here's a good reason why you're going to want to have to do this math, is to find out what you get here, unfortunately. So now they're calling this A sub n rather than T3. The first term is still equal to 3. And then I'm probably going to do some little math over here. So 5/4 minus 1 is 1/4. So this will be negative 6 times 1/4, and then the 1 factorial and the first power don't matter. So that's negative 6 over 4, which gives you negative 3 over 2. All right, when I plug in 5/4 here, again, 5/4 minus 1 is 1/4. Well, 24 times 1/4 is 6. I'm sorry, I got to square it first. 1/4 squared is 1/16, so this is 24. 2 factorial is 2 times 1 over 16. Well, that is 24 over 2 times 16 is 32. And 24 over 32, those are both divisible by 8, so that looks like it's 3 over 4. So plus 3 over 4. All right, for the last one, plug in 5/4 minus 1 is 1/4. 1/4 to the third power is 1 over 64. So I have 144 over 3 factorial is 6, and then times 1 over 64. All right, so got to do some math here. So what I would probably do is do 144 divided by 6 first. So that would be, looks like 24 times 1 over 64. Looks like those are divisible by 8. So 24 divided by 8 gives you 3, and 64 divided by 8 gives you 8. So the next term will be minus 3/8. All right, so again, it's a geometric series, so I'm basically finding the sum, so I need the ratio. That's why I got this. So hopefully you can see that what are you multiplying by to get to the next term? Well, the top is staying 3 every single time, so the top will just be 1. And then the bottom is going, there's a 1 here, so 1, 2, 4, 8, so you're multiplying by 2 on the bottom, so the ratio is actually -1/2, but the absolute value of -1/2 is 1/2, which is less than 1, so this one will converge, and it converges to, it's geometric, so the sum it converges to is a1 over 1 minus r. The first term was 3 over 1 minus the ratio, which again is -1/2. Negative negative a half becomes plus a half, and 1 plus a half is 3/2. Rather than divide by 3/2, multiply by 2/3. So your sum is equal to 2. So this series will converge to 2. All right, next we're going to look at a graph here. So a portion of the function h of x over 2 is shown above. Explain why h of x of 2 could not be the graph of f of x. Well, there's a couple of things I should notice about this graph. One is this graph is increasing, which would be a first derivative test. And it also looks like this is concave up, which is a second derivative test. So I need to kind of look at both of those things. All right, so probably the easiest way to do this is the graph of f. Oh, that's not an f. Graph of f. We know values at x is 1 from the table all the way at the top, which you can't see right now. That would be equal to h at, when I plug in 1, I get h of a half. And then if I plugged in 4 for f, or for x, I get f of 4 is equal to h at 2. Okay. Well, for a half here, for h at a half, I don't know anything about h and a half because there's no value here. But f of 4 is equal to h at 2, so h at 2 is shown on the graph here. And let me go back up real quick and take a look at that. So f at 4 is equal to h at 2, which is -9/4. So that's a possibility because it's below the x-axis. So that's a possibility. So now I want to look at 4 because I've ruled out 1 being a possibility for the graph, since h at 1, like I said, isn't shown on the graph here. But h at 4, that's a possibility that that could be -9/4. Whoops, I had a feeling I was going to do that. All right, so now let's look at the first derivative at 4, which is equal to h prime at 2. Let me see if I have that table. All right, I'm not going to scroll back up. I got that table in front of me. You can look at it as you do it. So that's equal to 3/2, which is greater than 0, which means increasing, which this graph is. So now let's look at the second derivative. F double prime at 4 is equal to h double prime at 2. And from the table, that's equal to -9/4, which is less than 0, which means that you should be concave down. And guess what? This graph is concave up. So you can say, based on concavity, h of x over 2 could not be the graph of f of x. Oops. Like that, okay? So here they threw in a little problem that really has nothing to do with series. It just has to do with plugging in the values and looking at the function value first, and then the first derivative, and then the second derivative. All right, this is our last one. This is obviously a graph problem. So they have a graph of g of x here. Usually they'll label it down here, but here they didn't. So we have a graph of g of x, which looks like this, and we have a tangent line drawn here at the point 2, 1. Okay. So the function g has derivatives of all orders of the values of f of x, which means I can take the derivative for forever. A portion of the graph of g is shown above, and the tangent line to the graph of f at x is equal to 2 is drawn there in blue. Let h be the function defined as h of x is equal to x minus 2 minus the integral from 2 to 2x of g of t dt. Find the second degree Taylor polynomial t2x for h of x centered at x is equal to 1. So I'm finding t2x here. All right, so I need the function value of h at 1, which is just plugging in 1. So 1 minus 2 gives you negative 1. And then minus the integral from 2 to, when I plug in 1 here for x, I get 2. And the integral from 2 to 2 is 0. So obviously that's just negative 1. So the function value is negative 1. And then I need the second derivative. So I need h prime, which I'll go ahead and do up here, at x. So the derivative of x is 1, derivative of negative 2 is 0, and then the derivative of the integral is just this function g. When I replace the dummy variable t with 2x in this case, chain rule applies, so I got to times that by 2. Okay. All right, now I need h prime at x is 1, so that's 1 minus 2 times g at 2 times 1 is 2. Well, g at 2, this is a graph of g, so g at 2 is just 1, and 1 minus 2 times 1 is 1 minus 2, which is negative 1, so the derivative is negative 1, and then this will be x minus 1 to the first over 1 factorial, which again, you don't have to write that, but I did in this case. All right. For the second derivative, derivative of 1 is 0, this will be chain rule again, so this will be negative 2 times the derivative of the inside is 2, which gives you negative 4, g prime at 2x. Plug in 1, you get g prime at 1. Well, this is a graph of g. How do I get derivative off a graph? Is slope of the line. So looks like if I pick this point here and maybe this point here, the graph or the slope of the line is up 1, 2, 3, and 1 to the right. So that's positive 3. Times negative 4 gives me negative 12. So it's the second derivative, negative 12, x minus 1 to the second power over 2 factorial. All right, and again, don't simplify it unless there's a good reason to. All right, for part B, explain why the second degree Taylor polynomial 1 plus 3, x minus 2, minus 5 over 2 factorial, x minus 2 squared could not be the second degree Taylor polynomial for g centered at x equals 2. Well, in this case, just looking at this term, the second derivative of g has to equal what? Well, that's your negative 5 right there, because it's be the second derivative, the x term to the second power over 2 factorial is the construction of that one. All right, so now how do I get the centered at 2 as x is 2? So I'm looking for g double prime at 2. Well, if I go to g double prime at 2, how do we get the second derivative off this graph, or what are we looking for is the concavity, and this is concave up at 2, and this is negative, so g double prime at 2 is actually greater than 0 because g is concave up at x equals 2. Thus, this is not the second degree Taylor polynomial. Okay. And I'm not going to write all that out. All right, for this last one, part C, and yes, we're almost done now. Consider the geometric series, sum of an over 2n factorial, starting at n is 0, where the first 3 terms of an correspond to the 3 terms for this. Find the summation of this when x is equal to 0. All right, so I'm going to start off with AN is equal to the first three terms, and the first three terms were -1 minus, this time I'm going to simplify it to just x minus 1, and then up above 12 over 2 factorial, well 2 factorial is 2 and 12 over 2 factorial is 6, so that'll be minus 6 x minus 1 squared. And now I'm going to be dividing that by 2n factorial. And if I write it all like that, then that's dividing them all by 2n factorial, right? All right, so if I plug in x is 0 first, this will be 0 minus 1 is -1. This will be 0 minus 1 -1 squared, which is 1. So this will be -1 plus 1, which is 0. And then minus 6 gives me -6. Actually, I don't think I want to write it like that. So this is the third degree Taylor polynomial. Well, let's go ahead and separate it out because the first term is when n is 0. So in that case, you get -1 over 2 times 0, which is 0 factorial. And then the second term is x minus 1. When I plug in n is 1, this 2 over n factorial becomes 2 factorial. And then minus 6, x minus 1 squared, plug in n is 2, that gives you 4 factorial there. Okay. Well, don't let this confuse you. 0 factorial is actually 1, so you're not dividing by 0 here, you're dividing by 1. So remember, 0 factorial is equal to 1. So that gives you -1. When I plug in x is 0 here, 0 minus 1 is -1, over 2 factorial is 2, so this is negative, which is positive 1 over 2. And then 0 minus 1 is -1 squared is positive 1. Minus will give you a negative. 4 factorial is 24, and 6 over 24 reduces to 1 over 4, so this will be -1/4. Okay. So that's at x equals 0. So at x equals 0, this is what I end up with. Well, this is a geometric series. Hopefully you can see you're multiplying by -1/2. So r is equal to -1/2. And I'm finding the sum, which again is sum is equal to a1 over 1 minus r. The first term was -1, so the sum is going to be -1 over 1 minus your ratio, which is -1/2. And because the absolute value of this is less than 1, I am allowed to use this formula. So that'll be -1 over minus a negative becomes positive, and 1 plus a half is 3/2. Flip that over, multiply by the reciprocal, and you get -2/3. And that's your sum that this converges to. So you could say converges to -2/3. Okay. All right, that is just about coming up on an hour, so a solid hour of serious problems. These are the kind of problems that you're going to see on the test. So hopefully you're writing this all out neater than I'm able to on my screen here. Have this ready for you for the test because the problems you're going to see that involve series, especially this year, have a good chance of looking very similar to this.